Good day, I'm Norman Wapper. In this video, we would like to set out some alternative framework for the fundamental theorem of algebra. Or actually the fundamental theorems of algebra that we talked about last time, because there were actually a couple of them closely related. So what I want to do is reposition these actual theorems to be much more algebraic, to not actually involve any analysis, at least in their statements, so that at least the statements of the theorems are completely algebraic and fit inside of algebra, really. In particular, that they should be logically frameable. So that's what we're going to do. We're going to lay out precise algebraic formulations of the fundamental theorem of algebra. This was actually first exhibited in my algebraic topology series quite some years ago. So it's really an enormous opportunity that we open up here, and I'm hoping that some viewers will take this up, because it's an incredible opportunity for some young people, or maybe not so young people, to make really serious contribution to mathematics. This particular theorem especially is of fundamental importance in mathematics. It really is a pillar of algebra, as the name suggests. It's crucially important. And so it's very, very, very important that we have a solid formulation and proof of this thing. Currently we don't have that, so this is an enormous opportunity for some young people to become rich and famous, or at least famous. Okay, so this is really amongst the foremost challenges in pure mathematics in the current era, and I think it's probably not much of an exaggeration to say that proving this result, really getting it on a firm basis, would be as important as any other single mathematical accomplishment in the, say, 20th century. It really is at that level. It's Fields Medal level, a kind of a challenge. Very, very important. So maybe you can do it. Alright, so our challenge is to set up this framework in a purely algebraic way. So really relying on the basic operations of addition, multiplication, subtraction, and division. No transcendental processes, no infinite processes being completed. So none of that implicitly under the rug, surreptitiously. Okay? Everything squared away, logical, finite number of operations. Okay, so the setup is that of rational complex numbers. So these are not the usual complex numbers. These are actually the true complex numbers. All right. So a rational complex number is what? It's an expression of the form a plus bi, where a and b are rational numbers. This is a rather quick way of introducing rational complex numbers. We will also, in a little while, show you some other ways of thinking about these things, which are perhaps a little bit more intuitive or in the line of data structures. But for now, it's familiar enough, I think, to most people. A plus bi, but a and b are rational numbers. That's the critical point. Okay. So these things can be added in the usual kind of way, and they can be multiplied in this particular way, which really amounts to the rule that I times I is a minus 1. So this bi times this di becomes a minus bd. And this creates a field. We won't say precisely what that means, but it's a field with the name RATCOM, say for rational complex numbers, which contains the rational numbers in the special case when the coefficient of I is 0. In that case, we get something which is just a rational number. So we can think about the rational complexes as being an extension of the rational numbers. While historically complex numbers were problematic, when it became apparent that there was a two-dimensional representation of them, then it was a little bit easier for people to visualize them and understand them. So this is sometimes called the Argand plane, where we take the usual xy plane and identify the y-axis with the I-axis. So we have usual rational numbers here and multiples of I in this direction. That allows us to visualize a complex number like 3 plus 2i as 3 in this direction and 2i in this direction. So it really corresponds to the point 3, 2 in a sort of affine setting. So we can visualize rational complex numbers as points in the familiar affine plane. And now here is the main measurement notion that we'll need. The quadrants of a rational complex number z, which is a plus bi, is the rational number q of z, which is a squared plus b squared. All right. So a squared plus b squared, that's the quadrants between these 2 points in the usual two-dimensional Euclidean plane. Remarkably, this quantity doesn't really get officially defined in complex analysis courses, which is really quite astounding because it's an absolutely central and fundamental notion. Unfortunately, most treatments of complex numbers start by saying, let's immediately take the square root of this and call this the absolute value of the complex number. We do not want to do that, okay? People, we do not want to use absolute value in this context because the square root involves really an infinite process. You have the square root of, in this case, for example, 9 plus 4 is 13, the square root of 13. That's not something that you can access in a standard way with only a finite number of arithmetical steps. But the quadrants, which is just 13, is of course very easy and pleasant to work with. So that's a big adjustment that one ought to make when one is studying complex numbers, to think about quadrants rather than absolute value. And 2 very important and useful facts about quadrants. First of all, that the quadrants of a complex number z is 0 precisely when z equals 0. So it goes both ways. If the quadrant is 0, then the complex number is 0, and easily to see that if the complex number is 0, then its quadrant is 0. And this is probably the most important fact about complex numbers from an elementary point of view, the fact that the quadrants is multiplicative. That quadrants of a product z times w, where z and w are both rational complex numbers, is the product of q of z times q of w. Okay, so we're not going to go too far in this direction for now. The main thing is to understand that we can extend polynomial algebra or arithmetic from polynomials involving rational coefficients to polynomials involving complex coefficients. And we can replace the idea of plugging in rational values with the idea of plugging in rational complex values. So for example, here is a polynomial. P of z equals z to the 5th minus 2z plus 3. Then, if, for example, we substitute the complex number 1 minus 1/2 I, we can sub that in here. That would involve taking the 5th power of this thing and subtracting 2 times it and adding 3. And one can check that the result of that is the complex number minus 3 over 16 minus 9 over 32i. So for example, if we were looking for a 0 of this polynomial regarded in this complex setting, then this would not be a 0 because the polynomial evaluated at it is not 0. But if we manage to find such a complex number such that we do get 0, then that's a 0 or a root of the complex polynomial. Okay, so now these true fundamental theorem of algebra statements that we're interested in, they really are going to be purely algebraic. So we want statements which are purely algebraic, that can be understood in principle by a primary school student. Doesn't know any calculus, no analysis, no complicated functions. You just know how to add, multiply, subtract, and divide, and they have learned a little bit about this complex number arithmetic. Okay, so there are going to be several such theorems. In the same way that in the previous video we had 2 different theorems, here there will be 2 different theorems plus a little bit more. And they have sort of some increasing sophistication. And I want to reiterate this very important point, okay? We have no proper proofs of these statements. Okay? None of the many proofs that have been given are logically correct, because they all implicitly, one way or the other, assume somewhere or another infinite processes. Right? One way or the other, if you look at all of the proofs, they're all doing this. And we want to avoid that. We want to understand the situation so deeply that we can see the essential algebraic aspect of them. So this is an incredible opportunity for smart, careful, and precise thinkers. 1,000 years from now, people will be jealous of you, of having this opportunity to be able to prove such an important, crucially important theorem, an absolute foundational aspect for pretty well all of algebra. That's waiting, that's in the future, that's to come. Maybe some of you can be involved. Very exciting. All right, so here's the first true fundamental theorem of algebra. And it's necessarily a little bit more complicated to state than the usual one because it's more precise and pins things down more carefully. Okay, so we pay a little bit of a price for being more accurate and staying in the algebraic world. So what is it? For any non-constant polynomial, p of z equals a0 plus a1z plus all the way up to anz to the n. We'll assume that this a sub n is not equal to 0 with n greater than or equal to 1. So it's non-constant means that the degree of this polynomial is at least 1. And these coefficients a0, a1 up to an, they are all rational complex numbers. So given such a polynomial, and given a natural number k, which is bigger than or equal to 1, the statement is that then there is a w equals a plus bi, a rational complex number, with the property that the quadrants of p of w is less than or equal to 1 over k. So you're given a polynomial, and then someone says let's choose k equals 10 or whatever. There's some particular k chosen, and then your job is to find an approximate 0. Not really a 0, but an approximate 0. What does that mean? It means a complex number, a rational complex number crucially, so that when you plug it into the polynomial you get this other complex number p of w. And when you take the quadrants of that, it's small. The quadrants being small means that the complex number is close to 0 on the page. And how close? It's at most 1 over k. Okay, so let's have a look at an example, because we like explicit, concrete examples. Here is a polynomial p of z equals z to the 6th plus 3z squared plus z plus 1. In the ordinary, say, rational number domain, this is what its graph looks like. It has some kind of shape like this. And it's quite clear that it's not going to cross the x-axis, so it doesn't have a traditional 0. And in times gone by, people would have said this function doesn't have a 0. But over the complex plane, we have a wider story, and we can get some approximate zeros at least. So let's see how that works. So the ingredients for the fundamental theorem of algebra part 1, as we've set it out, is a polynomial like this, together with some resolution level k, say k equals 30. So if we're given these two quantities, then we want to find a complex number w equals a plus bi, crucially a rational complex number, such that the quadrants of p of w is less than or equal to, say, 1 over 30. So we want that when we plug this thing into here, we're getting a complex number which is in quite a close proximity to 0. It's within a quadrants of 1 over 30. Okay, so I have found such a 0 for you, and here it is. It's minus 1/6 plus 1/2 I. If we take this complex number and plug it in here, so we calculate the 6th power and so on and make this calculation, then we get this complex number, 127 over 729 minus 13 over 648i. And if we call that thing v, then this complex number v has quadrants. Well, it's that thing squared plus that thing squared, and that turns out to be this 1045,945 over 340,12224. And they kind of line up here. So this is around 1 over 34, so it's going to be less than 1 over 30. So yes, indeed, This particular complex number has the property that Q of P of W is less than 1 over K, where K is our chosen resolution. So this works in this case. This is an approximate zero that we've been able to obtain. And this is all that we can ever do. There's nothing more than we can ever do here. Right? This is the typical story. We have a resolution level and we can try to get a complex number so that we have an approximate zero within that resolution. That's what the true fundamental theorem of algebra, part 1, tells us. So I hope you remember what the second version of the fundamental theorem of algebra was. It was that if you have a non-constant polynomial, that it factors into linear factors over the complex numbers. Okay, that is not a true statement. That is just not a true statement. But here is a, well, possibly true statement. We're almost sure this is true, but we don't actually have a proof. So the true fundamental theorem of algebra number 2. For any non-constant polynomial p of z, so it's the same as before, a0 plus a1z up to anz to the n, an is not equal to 0, and n is greater than or equal to 1. So it really is a non-constant polynomial. It's of degree at least 1. And the a0, a1 up to an coefficients are all rational complex numbers. And given also any k, a natural number, greater than or equal to 1. So given that data, the claim is there are rational complex numbers w1, w2, up to wn, such that the following rather onerous looking thing is true. So if something is less than or equal to 1, okay, it's the same kind of thing. And it's the quadrants of something. So what are we talking about here? We're talking about the difference between the original polynomial and this new polynomial that's created by taking the factors z minus w1 times z minus w2 all the way up to z minus wn, and multiplying all of that by an, that highest coefficient there, which we assumed was non-zero. This particular combination is meant to guarantee that the highest degree terms in both of this expression and this expression are equal. They're both equal to a sub n times z to the n. But the highest power of z here will be z times z all the way up to z, there'll be n of them, times a sub n. So when we take the difference, then that will disappear. And what do we mean by the quadrants of a polynomial? Because inside here is no longer a complex number, it's actually a polynomial. So I have to tell you what the quadrants of a polynomial is. Okay, so very important. Where here is a polynomial, b0 plus b1z plus all the way up to bn z to the n. We're to define the quadrants of this polynomial to be the sum of the quadrants of the coefficients. So q of b0 plus q of b1 plus q all the way up to q of bn. So the sum of the quadrants of the coefficients is what we regard to be the quadrants of the whole polynomial. Now, these things are always going to be positive rational numbers. So when we add up all of these things, there's going to be another positive rational number. And our claim is that we can find these complex numbers w1 through wn so that the polynomial p of z is not maybe a product of linear factors, but it's close to being a product of linear factors. That's what this statement is saying. It's saying that there's not that much difference between the polynomial p of z and this product of linear factors. And it makes precise what we mean by being close to. Okay, it's really a very geometrical thing. This is almost like an n-dimensional or n+1 dimensional space, and it's really natural just quadrants in that n+1 dimensional space. So geometrically, this is a very natural thing to do. So this is the second version of our fundamental theorem of algebra. Purely algebraic, no real numbers in sight, everything just rational complex numbers. All right, so let's have a look at an example. The same polynomial that we've already looked at, p of z equals z to the 6th plus 3z squared plus z plus 1. And we're going to illustrate this second fundamental theorem of algebra, the true one, which asserts that we can approximately factor this thing into linear factors. There will be 6 of them because it's of degree 6. We cannot precisely factor this thing into linear factors. That is a dream that we have to give up on. But we can aspire to doing it approximately. And I've actually done that for you within a certain resolution. So here is a 6-degree polynomial. It's actually a product of 6 linear factors. And I'm looking now at the difference between the polynomial that we started with and this particular product of linear factors. That difference, let's call it r of z, we want to make that small. Okay, so let's have a look at these factors. This one here we recognize. This is z minus that same number that we saw was an approximate 0 of p of z. That's typically the strategy. You use z minus an approximate 0 for these linear factors. So there is that z minus 1/6 plus 1/2 I. And here's a similar kind of thing, almost the same, except that we've replaced this thing with what's called its conjugate, or complex conjugate, where you replace the sign here in front of the I term with its negative. So that's a thing that happens typically in this kind of situation. But aside from these 2 linear factors, we've also found some other ones. So here is z minus 22 over 21 plus 10 over 11i, and z minus its complex conjugate. And we're also multiplying by z minus 8 over 9 minus 7/8 I times z minus the complex conjugate. So these now are 6 approximate zeros to p of z. They're complex numbers that have the property that if you plug them into p, you're going to get some small complex number. And if we form this product of linear factors with these approximate zeros, then we have an approximate factoring of our polynomial. And we can see how close that is by taking this difference and computing its quadrants. Now when we take this difference, you'll notice that there's no coefficient here because this polynomial is monic. It has a coefficient of 1 in the highest power, so there's no need for us to put another coefficient there. And when we take the difference, we're going to drop the z to the 6th terms. There are not going to be any more of those. We're just going to have terms starting from z to the 5th and down to the constant term. And when we take the quadrants of that, what we're doing is we're taking the sum of the squares of each of those coefficients. And I've got my computer to calculate that for you, and we get this number here. Okay, and I've tried to line them up in such a way that you can kind of see it's basically like 9 over 247. That's almost like 1 over 24. And that's just a little bit less than 1 over 25. So if our k value was 25, then this would be a linear factorization of the polynomial, which is approximate, but which is within the resolution of k equals 25. I think it's quite interesting. I think the numbers are interesting. I think it's pleasant and also curious that the zeros that we're getting here are relatively simple fractions, right? They're not very big. This is a reasonably decent sized polynomial, and it's kind of curious that we can get to this pretty good approximation, because this is actually the sum of all these 5 or 6 quadrances for a total of less than 1 over 25. We're doing pretty well with relatively simple-minded factors, you might say. Which brings us to the interesting question, okay, so just how can we generalize this kind of thing? You know, given a polynomial and we understand its coefficients, given a k value, how complicated do these zeros have to be? In other words, how big are the numerators and denominators typically going to be, so that we get within the resolution required? This is an example of the different kind of question that arises when we give up on our abstract, theoretical pie in the sky kind of explanation of what's going on and return to a more concrete, computational, let's see what actually happens point of view. So we give up on the dreaming, we face the reality, but more interesting questions arise. We see more. we get in more contact with real mathematics. So I'm hopeful that when we do find a proof for these theorems, that those proofs will have a strong computational bias. I think it will involve having more insight than we currently have. So if you're aspiring to prove these things, the first thing you should do is have a good look at the classical proofs. There are a lot of great ideas in those classical proofs. Okay, and you will want to understand the basic ideas there. There's all these topological ideas. And then you want to wrestle with how are you going to restate those topological arguments without making all these real number assumptions about continuity. How you can get it down to just algebra. It's a very major challenge. And I think it really, it'll probably be useful to keep in mind this computational question. It's not just a question of proving these things, but really what we'd like to do is to have some understanding of how we find those zeros. Given a polynomial, given a k, how do we actually find an approximate zero of that degree of accuracy? What do we have to do? Can we actually give a computational proof of these theorems? That would be really fabulous. And I also want to mention that there's another challenge sort of lurking in the background. After you start thinking about this for a little while, you'll realize that the first two theorems that I've given you are not the end of the story. There's naturally some further extensions that you want to enunciate and pin down. So I'm not going to say what those are at this point. I might do later on, maybe in my algebraic calculus course, which I'm thinking about and sort of slowly working on. But anyway, there's some fundamental theorem of algebra, part 3 and part 4, that are sort of out there that are worth sort of investigating, and I'll leave it to you to maybe figure out what those might be. So I know that there will be a fair number of mathematicians who are not going to be happy with this new direction. It's destabilizing, it's disconcerting to realize that something that you had accepted for a long time was in fact not really entirely correct, that there's this major logical gap there. But nevertheless, it's an opportunity for a lot of invigorated discussion and development in the subject, I think. In our next video, I want to talk a little bit more about the fundamental theorem and its applications to algebra. In particular, how it changes our point of view towards fields. And I want to have a look at a very specific example coming from roots of unity and so-called cyclotomic fields. I'll be able to do that without a lot of background, and that'll give you a good understanding of why we really need to think about algebra in a majorly different way now that we sort of understand these difficulties with the fundamental theorem of algebra. So I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.